Hello everybody, today I'm going to explain the solution to the third problem from the 2025 US Open Contest in the Silver Division, the problem ski slope. In this problem, we are given a trip, we are given a tree where Bessie is going to a ski trip with her friends, and we are given a tree structure where we know for each waypoint that there is a ski run starting from I and ending at PI. So basically kind of like a graph where we know for each node the parent, and then obviously we have the root in node 1. And each of the friends will choose a node to start at and then follow the runs downward all the way until waypoint 1. And basically the enjoyment each friend gets is equal to the sum of the enjoyments of the runs they follow. And now for each friend we know the skill level and the courage level, and basically these things limit the friends to selecting the points in such a way that they can actually take at most CJ runs with difficulty greater than SJ. And very important here to observe that they must reach waypoint 1. Actually, when I first solved this problem, it took me half an hour of reading the problem and thinking at a way more complicated version until I realized that the answer for the first sample is 0. And I was thinking that why can't they go from 4 to 2 and the difficulty is 10? And then I realized that they must reach the root. So this is why it's very important to pay attention to the statement of the problem. And now, given that we know that the friends must start somewhere in such a way that they can actually reach the root, so this makes the problem easier. Now, for a given query, we can actually start a traversal from, let's say, the root and go down the tree using the edges given in such a way that we can actually count how many extra trips they have to make, and then stop whenever let's say the number of obstacles, the number of bad spots is bigger than the limit. So basically it all comes down to traversing the tree in such a way that we actually fulfill the restriction regarding the limit in terms of uh, the courage. Now, because there are way too many queries for us to be able to reliably do this, since it would take way too much time and we would run out of time. Now, we want to find a way to maybe solve the queries in a manner that helps us maybe use some of the answers for later on in the problem. And a way which is very common in problems like this is to sort the queries by some criteria. And the criteria I used was to sort them in increasing order of the skill level friends have, because a friend will know skill will basically have to take courage jump every time until they will no longer be able to do that. And there are only 10 let's say moves they can make that are outside of their skill level, so this is also something that plays in our strengths. And because of this reason, we can actually, if we think at the broader structure of the tree, so if we have a tree, then if we are at the root, we know that no matter what we do, then we will be able to reach the root. And then like we talked about in the slower solution, then we can keep track for each query of that sort of count and see how it goes. But obviously we can't do that. So now a very important thing worth considering is that when it comes to let's say problems in which we can sort the queries, we want to be able to compute as we go down the tree using a DFS. We want to keep track of the lowest skill level required to be able to reach a certain node with at most, let's say, one skip, two skips, and so on. So basically, we want to keep maybe track of, let's say, 10 multisets or even 11, because there is also the chance of having no skips at our disposal. And for example, assuming that we do this for, let's say, two skips at our disposal, we will keep track of these weights from these edges. And whenever at some point the multi-set of weights is larger than the number of skips we have at our disposal, we will always want to remove the smallest edges, because the smallest weight edges will be those which will hinder the, let's say, the skill with the friend with the smaller skill. And basically this means that someone with a larger skill will have no problem sailing through them, skiing through them, and thus whenever we have a edge with a small weight, we can increase the minimum required weight to be able to use this path. Because once we have a path, we establish that it works, we can add it maybe in some data structure or keep it in maybe some prefix sum and have it computed as part of the maximum, as I will show later in the problem. Now, another thing we're considering is that whenever we are done with the path, we will have to go back up the tree, restore the state of the multisets as they were before that point, and then do the same thing for every branch of the tree. So for every branch of the tree, we will have to repeat the process. Now, this algorithm, if implemented properly, something I will go in more detail as in the next few minutes, because implementation is quite complicated. If implemented properly, this algorithm will run in something like n times 10 times log n or something like that, because we will have to keep 11 multisets and have some binary searches also. So there is quite a bit of computational complexity we have to deal with in order to have a proper implementation. So let me show you what I mean with this. So as you see here, when I read the input, I first keep track of the tree as it is, and also have an initial DFS where I compute for every node the sum of the excitement values from the root until that node, as well as the level of the vertex. I thought I might have to use it somehow, but I don't think I ended up using it in the end. Now, after doing this, I actually read the queries and I sorted them by the weight of, by the skill level the friend has, because I will want to process them later on as I acquire the answers through the other DFS. Like you see here that I keep track of some 2D array which stores the highest amount of excitement a friend gets if they have at most I skips and they have a strength equivalent to the strength of the jade friend or something. But let's focus on the second DFS. So in the second DFS, I keep track, I want to find for every node the minimum skill level they need in order to make it to that node with at most I skips. So obviously the number of skips goes from 0 to 10, and this is why I kept 11 multisets. And I have this amount of ij, the maximum strength, if the strength will be equivalent to the one from the jade query in the sorted order, and we can make at most I mistakes. And basically I also have the query values where I know for each query the strength of the friend, the amount of skips, as well as the initial position in the query sequence. Here I do a binary search for each of these queries to see exactly where would each of these friends end up at if the query would involve I skips. And then I keep track of this vector with minimum values, because it tells me the minimum amount of strength required in order to reach the node with I skips 0, 1, 2, all the way until 10. And then here I, for every child of the current node, I insert the current, let's say, skill level, the current skill level required to pass the uh, track without a heap of courage. And for every number of skips, I also check to see how much do I need to uh, remove in order to let's say keep track of the current amount of changes. So basically to see exactly what slopes have to be removed and how exactly things change as we go along the minimum values. And again, I had this minimum values array. I have a copy also. And then after I call the DFS, it's very important to undo the changes because you might have multiple children and you want to keep the same state for every child. And this is why I had these calculations here to make sure that the removals and the obstacles are being implemented in such a way that you don't ever have any trouble with them. So again, a very useful thing to have in mind, especially as we work along the way to solve the problem, because a very precise implementation is required in order to solve the problem. And even though the problem may seem complex at first, it's just a lot of relatively easy things to do, but they add up, and it's very important to pay attention to each and every one of them. And as you see here, it's the longest code by far in this contest. But again, the idea itself also had a bit of difficulties. So one had to be very careful when it comes to combining the ideas, especially for the thinking part and the implementation part. So in order to summarize for this problem, we had to observe that all the routes must end in the root. And for every amount of skips, we want to have a traversal which tells us the nodes we can reach, such that we are allowed to have a certain amount of skips. And by sorting the queries, we make our life easier as we just observe for a given query how much more we can go downwards as we progress through the tree. And this can be done either through the DFS or with some BFS. Again, a graph traversal is required in order to get the problem done. If you enjoyed watching this video, please like it, subscribe to the channel and press the bell button in order to stay notified with everything I do in the channel, especially as the season came to an end and I am planning to create a lot more content, be it solutions to problems, also educational materials, code forces problem solutions, and many other cool stuff. In addition, if you or someone else you know is interested in joining my tutoring program and working more closely with me, please check out the links in the description for ways to be part of the tutoring program, which helped over 20 students achieve promotions just this season alone. Last but not least, I recommend you also checking all the other resources I have in the description, be it for this contest or the past contests from this season, as I made an impressive amount of 27 videos, 9 in December, 6 in January, 6 in February, and 6 during the US Open. Until the next time, good luck with your practice, and I'll see you in the next video. Cheers!